Hello, Eastview Scholars, and welcome to this edition of Sharp Shorts, where we're going to discuss matter and change. As we've started this unit, one of the things we wanted to define was what's matter. Well, matter is everything. Matter is everything around you. It's the air, it's the food you eat, it's the cool Packers clothing you wear. It's everything. As we looked at our first unit and defined density and matter together, matter is anything that's made up of atoms, and those atoms then take up a certain amount of volume. So matter is anything with massive volume, which is everything around us. Our point more in this tutorial is more to break down matter into what is it? How can we, since matter is everything, how can we easily break it down and classify it to understand it better rather than this massively broad subject? And part of that reason is that's what this course is about. Chemistry is about the study of matter and how it interacts, and how can we incorporate that and use that and our knowledge of how things interact. So let's just first break it down into saying what's a pure substance and what's a mixture. And it really breaks down to this. A pure substance is really just one thing that can't be separated out anymore by physical means. A mixture is two or more substances that you can separate out by some physical means. So pure substances would be elements or compounds or molecules. Compounds, molecules, we'll use that term interchangeably. But those are things that you have just one type of element, one type of atom making that element. You have a big pile of sodium chloride. Yes, it's a compound, but you would have to use some sort of chemical means to separate the sodium and the chlorine for the most part, or at least to permanently separate them. Whereas a mixture is just what it is, two or more of those things that through different methods I can separate them out. Okay? Let's take a look at this chart. So here's our definition. Matter is everything around us, and as we'll talk about shortly, all matter has three phases: solid, liquid, and gas. You can see we've defined pure substances here as anything that is either an element or a compound. And don't worry whether we talk about binary or poly-elemental or what are called polyatomic compounds. But the idea here is just to understand that a pure substance is either can be elements or compounds. Mixtures, on the other hand, are mixtures of multiple substances. The two things we're really going to focus on are homogeneous and heterogeneous. Homogeneous means uniform. Think of Kool-Aid. I mix the water, the Kool-Aid powder, and the sugar, and I stir it all together. It looks like one big pitcher of colored water. That looks uniform throughout. Whereas a heterogeneous mixture, like a granola bar or a cookie, or if I dipped a jar into a pond and got all the rocks and the mud and everything with it, that would be a heterogeneous mixture. We're not going to talk about composite materials or colloids that much. Especially this. Colloids are interesting. While milk is labeled homogeneous and does look uniform, if you were to really look at it, there's fat droplets suspended all throughout, kind of floating, although you can't see them. That's more of a colloid. And there's some cool stuff that maybe we'll show you in class, but it's not a big concern. The big understanding is that you have homogeneous and heterogeneous mixtures. Okay. And then what we'll be doing, or one of those things that we have to look at, and part of your big challenge lab this time when you get four substances you have to separate, is if I have a mixture, what technique can I use that will allow me to separate out those components? And as like in your lab, how can I do it accurately? And really it's just working on the properties that we're going to talk about next of that substance. Would something in the heating, cooling, filtering, drying, sorting, or dissolving of that substance allow me to separate it from what it is mixed with? Now, some of this stuff, you can see the properties. If it was a metal that had magnetic properties, then I could take a magnet and pass it over and probably separate out from everything else in, say, a mixture pile of dry stuff. I could pull that out with a magnet and separate it out that way. A lot of times what we're doing is filtering and evaporating. Filtering, as you can see right here, is simply a great way to separate liquids and solid components. And all I do is have a funnel with some filter paper. I pour through all the mixture and rinse through the mixture. The solids and stuff get trapped in the filter, and what's called the filtrate then passes on through, and that would be the water, whatever liquid was basis of the solution, and then anything that has remained dissolved that was too small to stick in the filter. So this is a size, working on a property of size. It's often coupled with evaporation. I could then take this filtrate and put it over a flame or over a Bunsen burner on a hot plate and evaporate off the water, and anything dissolved then will reform as a solid. And so that's often evaporation is used, which is working on the boiling point of the water and changing its phase and leaving whatever was dissolved in the water, reforming it back into the compound it was before it was dissolved. Decanting is very much like kind of filtering. Really, it's often done when I want to do something with the solid stuff and separate it from the liquid. So rather than pour it through a filter, I just let it all settle very carefully and then carefully pour off the liquid. And then I have the solid substance in the beaker, and I can continue working with it. Another boiling point, like evaporation, is distillation, often used to separate especially liquid mixtures, where it works off all their different boiling points. Centrifuge and chromatography, again, are two things that work on size, whether through spinning and using force to kind of separate stuff out, or whether using some sort of filter or DNA gel or something to separate it on size. That idea in the lab that you have to do to separate stuff has you looking at the properties of matter. And so here, if we look at this, what determines something as a physical property, which allows us to look at ways to separate it, or a chemical property, which allows us to look at ways to use it in a reaction. Well, just like physical or chemical changes, physical or chemical properties are based on what it is. And after I see, even if I do something to change that property, will it stay the same, or will it change the identity of the stuff I'm working with? If it's not going to change the identity, then it's a physical property. If it is going to change the identity, and this is what a chemical change is, if it's going to change what I started with and actually change it into a new substance, then that was a chemical property or chemical change. And you can see by just looking at the chart is how does the substance react in the presence of air or an acid or water or bases or any other chemical. If I mix them together and I get a chemical change, then that was a chemical property. Whereas for the physical properties, whether they're color or taste or melting and boiling point, or even mass or volume, those things, even though I might say increase the mass or something like that, is not going to change what it is. Okay, say refined sugar. The color of refined sugar is the normal stuff Mom bakes with, and you see in the cupboard often, or that you might throw over your cereal because there's not enough sugar on it, is white for the refined processed sugar. No matter how much of that stuff I have, it's going to stay white, and it's going to taste the same all throughout, even if I dissolved it or did something with it along that line. Melting point and boiling point for a pure substance is a constant number, because that's what that pure substance has. So like water, pure water will melt at 0 degrees and boil at 100. And that will stay the same unless I put something in the water to change it. Okay. So that leads us to, if those are the properties, then how can I determine a physical or chemical change? It's not always easy. Sometimes it is, sometimes it isn't. If I'm just melting some ice or freezing some ice cubes or boiling some water, I'm just going through a phase change. That's not a chemical change. I'm not changing the substance. The water is remaining water, even if I just heat it up a little bit or cool it down a little bit. That's not going to change. If I boil it off and let it all evaporate away, that's not going to change what it is. That's what a physical change is. I dissolve stuff. In making Kool-Aid, I dissolve Kool-Aid powder and sugar in water. The sugar still retains its sugar properties and tastes like sugar. The water still retains its properties and tastes like water. The Kool-Aid powder still, even though it's dissolved in the mixture, retains the properties of what that powder has as far as flavor and everything else. So physical changes are things that don't change what the substance is. Chemical changes, on the other hand, do change what it is. You've had a reaction. You have not only broken bonds, but you've reformed bonds and made a new substance. Now this is where the difficulty can come in, because a color change could be a physical or chemical change. You really have to understand what you're working with and its properties and what you mix together to understand that. It certainly can indicate a chemical reaction in a new substance. Same thing for bubbling. Boiling water bubbles, but I'm not changing the water. But if I mix two things together and I see all of a sudden it starts bubbling and I haven't added in any extra energy, that would be a good chemical sign. Temperature change, again, not heating it, not putting in it, but just mixing two things together, and all of a sudden I watch the temperature rise in the mixture. That means a chemical reaction has probably occurred. You know, turning cloudy. I mix two clear liquids. All of a sudden it's cloudy and I see this solid stuff falling to the bottom. That means that I broke the bonds of the stuff I had. I rearranged. One of the new substances wasn't able to dissolve in water, so it formed what's called a precipitate and fell down to the bottom. So that would be an indicator of chemical change, that a new substance has been formed. Last thing we want to talk about in the big picture are those states of matter. And while there's 4, our focus is going to be on solids, liquids, and gases. The states of matter all have the same state of matter, and you can see what they're really dependent on is pressure and temperature. Okay? As you can see here, and temperature, of course, a big driving factor. Pressure is a big factor in between the gas and the liquid phase as things vaporize or condense. It can have some play into melting and freezing, but that has to be a very high pressure and stuff like that. Anyhow, so you have these different phases, and we know things about this from earlier science. Solids have a fixed shape and a fixed volume. You can't compress them. You know, you've seen crystals form, you've seen, you know, solid cubes, whatever. You can't compress them, you can break them, whatever. Liquids, on the other hand, have a definite volume, but they don't have a definite shape. Liquids take the shape of the container they're in. Well, they're at a little higher, depending on the substance. All substances, it's at a higher energy level. It's got more heat, more energy to it. They're moving faster. And so some of these intermolecular bonds that are there get broken, and that gives it a little more loose fluid structure. You still can't compress it, but it is not the fixed shape and volume of a solid. Now gases, they have no shape or volume. They fill evenly the shape of the container. They can be compressed. It's the one substance that can, because you have broken all these intermolecular bonds. They are essentially flying free on their own. And that leads us to our final question, is then, how does kinetic theory explain the different properties of each phase? Well, here's essentially what kinetic molecular theory is. Particles of matter are always in motion. Okay? And they are, even for solids. Solids are always just vibrating in place, but they're at low energy levels. They come close together, and they can form these intermolecular bonds that give them their crystal structure and the properties that they have with that. As I increase the energy, whether by adding heat or electricity or something else, I start breaking some of these bonds. They start moving faster. Temperature is defined as average speed of the molecules, so they're moving faster. So while I haven't completely separated them out, and there are some intermolecular bonds, it gives it a much more fluid state that allows it to take the shape of its container. And if for wherever I hit the boiling point or the gaseous phase of a substance, all those particles have now been separated. They're all flying around independently of each other. And really this was the basis of kinetic molecular theory was looking at the gases. And you can read the 5 postulates that tell what things are. We're not going to spend a lot of time on them right now. The important thing is to understand that we have the different phases, because as we increase the temperature, as we increase the average speed, we start breaking some and changing some of those bonds, those weak intermolecular bonds and stuff that hold things together. And by the time we get to gaseous phase, we have essentially all these independent little gas atoms flying around on their own. And that's what this is really, for us at this point, the most important thing is that kinetic energy is based on temperature. The higher that kinetic energy, the more you're heading towards gas phase, or eventually you hit gas phase. The lower that energy level is, then you're going to condense into a liquid and or a solid. And then when we get to gases, we can discuss the rest of this. It's just understanding that the whole theory of why phases are what they are started with gases, because at that point the atoms are independent little particles. So that's your background on what matter is, how to separate it, how to break it down and understand different parts, and why you have different phases because of their movement of the molecules and the average energy. So Scholar on Eastview